General relativity step by step. I'm going to go back to my equation of state which I had on the previous screencast, which was true for a perfect gas. d by dt of a cubed equals 0. And I'm going to ask, what about a photon gas? The universe has had different epochs, and in different times in the history of the universe, different source terms dominate, and sometimes the matter dominates, and sometimes the photons dominate, and sometimes the vacuum energy dominates. But what I'm going to do is think about a photon gas, which is typically appropriate for the very early universe, and we'll see when the different effects kick in. For photon gas, the stress energy tensor Ij is equal to rho 0, 0, 0, 0, and it's rho 0 over 3. It's diagonal, if it's isotropic, I guess. So it's like a perfect gas, but with the pressure equal to rho 0 over 3. So it's right on the very limit of the weak energy condition, I guess. Okay, so what happens to our equation? Well, let's write it out. We've got d by dt of rho 0 a cubed plus p0 d by dt of a cubed equals 0. And into this I'm going to substitute that p0 equals rho 0 over 3 and just see what happens. Okay, well that's rho 0 dot a cubed, that's differentiating that term, plus 3 rho 0 a squared a dot, differentiating that term, plus rho 0 over 3 times 3a squared a dot equals 0. Right, so that means that rho 0 dot a cubed plus 4, because the 3's cancel here and here, I guess, jong jong. 4 what? 4 rho 0 a squared a dot equals 0, and then I'm just going to multiply by a. Equals 0. And so that's a total derivative now. So d by dt of rho 0 a to the power 4 equals 0. And so what that tells me is that rho 0 a to the 4 equals a constant for a photon gas. Well, again, it's the same deal as with the previous equation. It kind of looks obvious. Of course, if you have your little control volume and you expand it so it's slightly bigger, then of course the temperature goes down, the energy density goes down according to a cubed. And in this case, because it's effectively done work on its surroundings, it goes down by another factor of a. So this is a kind of classical result, but again, it takes work to derive it, and that work is a clue that it is a non-obvious equation. This is not obvious because it's got density, and the density has got gravitational interaction between itself and the between the inside and the outside of our little control volume, and it's not obvious how that gravitational interaction is going to affect your equation of state. Nevertheless, we've got this nice little equation that rho 0 a to the 4 equals a constant for a photon gas, which is beautiful. I'm going to stop there. Stop.